February 23rd, 1945. The ruins of Düsseldorf. Staff Sergeant William Hendricks crouches behind the shattered remains of what was once a bakery, watching his Sherman take its fifth direct hit from German Panzerfaust teams hidden in the rubble. Each shape-charged warhead detonates against the hull with a sound like thunder tearing steel. His crew evacuated after the second hit, certain their tank would be destroyed. But the Sherman sits there, smoking but intact, its welded hull holding together in ways that should be impossible. 300 yards to the left, another Sherman, an early production model with a cast hull, burns furiously after taking a single Panzerfaust strike. The difference between these two tanks, between survival and destruction, comes down to a modification that Army Ordnance had rejected 18 months earlier as impractical, expensive, and unnecessary. In the summer of 1943, a civilian metallurgist named Fisher Elmore, working at the Chrysler Defense Arsenal, had proposed something that military engineers considered absurd: replace the Sherman's traditional cast hull with welded armor plate. The casting process had been perfected over decades. It was proven, reliable, and produced hulls that military doctrine considered adequate. Welding was a shipyard technique, unsuitable for the precision demands of tank construction. The mathematics of stress distribution didn't favor it. The metallurgy was questionable. The production challenges were insurmountable. But Elmore had seen something that bureaucracy missed. Cast hulls, for all their traditional reliability, contained microscopic flaws that became catastrophic weaknesses when subjected to the focused violence of shape-charge weapons. Every casting carried invisible stress points where molten steel had cooled unevenly. These points became fracture lines when German hollow-charge warheads struck home. A welded hull, properly executed, could distribute impact forces across a continuous steel plate, preventing the catastrophic failures that sent crews to their deaths. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The spring of 1943 brought a recognition to American armored forces that would reshape tank production for the remainder of the war. The Sherman tank, backbone of American armored divisions, was meeting new threats that its designers had never anticipated when they finalized specifications in 1941. German infantry anti-tank weapons, particularly the Panzerfaust and Panzerschreck systems, were proliferating across European battlefields with devastating effectiveness against Allied armor. Major Daniel Erickson stood in the tank recovery depot outside Palermo, Sicily, examining the remains of 7 Sherman tanks that had been knocked out during the previous week of fighting. The pattern of damage told a story that transcended simple battlefield losses. 5 of the 7 tanks had been destroyed not by German tank guns or anti-tank artillery, but by infantry portable weapons that cost a fraction of what a tank destroyer required. More troubling, the hulls showed fracture patterns that suggested structural failures extending far beyond the immediate impact sites. A Panzerfaust warhead, weighing roughly 3 pounds and fired from a disposable tube, carried a shaped charge that could defeat armor through focused explosive force rather than kinetic penetration. When the warhead struck, it created a superheated jet of metal particles traveling at velocities approaching 25,000 feet per second. This jet punched through armor plate and sent fragments ricocheting through the crew compartment with lethal effect. But Erickson noticed something more disturbing in the wrecked Shermans before him. The cast hulls weren't just penetrated at the impact point, they were cracking along stress lines that extended inches, sometimes feet, from where the warhead had struck. The molecular structure of cast steel, formed by pouring molten metal into sand molds and allowing it to cool, contained internal stresses that became visible only under extreme force. These stresses created weak points throughout the hull where the crystalline structure of the metal had formed unevenly during cooling. Technical Sergeant James Morrison, an armored recovery specialist who had served in North Africa before the Sicily campaign, described the problem with the bluntness of a man who had pulled too many dead crews from burning tanks. Cast hulls, he explained, were never truly uniform in their internal structure. The cooling process created areas of greater and lesser density, places where the molecular bonds were stronger or weaker. Under normal stress, these variations meant nothing. Under the focused violence of a shaped charge detonation, they became fault lines along which the entire hull could fail. The implications for crew survivability were stark. A Sherman struck by a Panzerfaust might survive the initial penetration, but hull fractures could compromise structural integrity, damage critical systems, or create secondary projectiles from fragmenting steel that killed crew members far from the impact site. German infantry had learned to target Sherman hulls specifically because these infantry weapons could achieve kills that would require much heavier anti-tank guns when fired at the turret. Intelligence reports from the European theatre confirmed that German tactical doctrine was evolving to exploit American tank vulnerabilities. Panzerfaust teams received training in targeting hull sides and rear areas where armor was thinnest and where shaped charge weapons could achieve maximum effect. The hollow charge warhead design meant that armor thickness mattered less than armor quality. A 3-pound Panzerfaust could defeat armor plate that would stop anti-tank gun rounds, weighing 10 times as much, provided the impact angle and hull characteristics favored penetration. Ericsson compiled his observations into a report that reached the Army Ordnance Department in late July 1943. His conclusions were carefully worded but uncompromising in their implications. Sherman tanks with cast hulls showed structural vulnerabilities when engaged by shaped charge weapons. The fracture patterns suggested that alternative hull construction methods might provide improved survivability. He recommended immediate investigation of welding techniques as a potential solution. The response from ordnance bureaucracy reflected the institutional conservatism that had characterized American tank development since the program's inception. Cast hull construction represented decades of engineering refinement. American foundries had perfected the casting process to the point where hulls could be produced with remarkable consistency and speed. Chrysler, Fisher Body, and other manufacturers had invested millions in casting facilities specifically designed for tank production. Shifting to welded construction would require retooling entire production lines, retraining workers, and validating completely new manufacturing procedures. The technical objections carried weight that transcended mere bureaucratic resistance. Cast hulls were created as single pieces, eliminating the hundreds of potential weak points that welding seams represented. A poorly executed weld could fail catastrophically under combat stress, creating vulnerabilities far worse than any flaws in cast construction. Welding thick armor plates required precise heat control to prevent warping, specialized electrodes to ensure proper metal fusion, and quality control procedures that would slow production at a time when American armored divisions needed tanks faster than factories could build them. Fisher Elmore entered this debate from an unexpected direction. A civilian metallurgist working at the Chrysler Defense Arsenal in Detroit, Elmore had spent 2 decades studying metal fatigue and stress distribution in automotive and industrial applications. His background was bridge construction and pressure vessel fabrication, fields where welding had long since proven superior to casting, for applications requiring maximum strength-to-weight ratios. When Ericsson's report circulated through technical channels, Elmore recognized patterns he had seen in failed industrial equipment. Cast structures, Elmore argued in a memorandum that would later become famous within engineering circles, contained inherent limitations that no amount of process refinement could eliminate. The physics of molten metal cooling in a mold created microscopic stress points throughout the casting. These stresses were manageable under gradual, distributed loads, but shaped charge weapons delivered force in a manner fundamentally different from conventional projectiles. The focused jet of superheated particles created shock waves that propagated through the hull structure, finding and exploiting every weak point in the crystalline matrix. Welded construction, properly executed, could eliminate these inherent weaknesses. Instead of pouring molten steel into a mold and hoping it cooled evenly, manufacturers could cut armor plate from rolled steel stock that had been work-hardened during production. These plates, welded together with appropriate techniques, would create hulls with continuous, predictable metallurgical properties. The welds themselves, if executed correctly, would be stronger than the surrounding base metal. Stress distribution would occur along designed load paths rather than random cooling patterns. The resistance to Elmore's proposal came from multiple directions simultaneously. Production managers calculated that converting Sherman hull manufacture from casting to welding would reduce output by 30 to 40% during the transition period. Quality control engineers questioned whether welders could be trained to execute the hundreds of critical seams required for a tank hull with sufficient consistency to ensure battlefield reliability. Military procurement officers worried about the cost implications of scrapping existing casting infrastructure and building new welding facilities. Most significantly, combat commanders questioned whether the theoretical advantages of welded hulls justified disrupting the flow of replacement tanks to units that were losing vehicles faster than current production could replace them. The summer of 1943 saw American armored divisions preparing for operations that would require thousands of tanks. Any reduction in Sherman availability, even temporarily, could compromise operations that were already planned and resourced. Elmore found an unexpected ally in Colonel Henry Sterling, an Ordnance Corps officer whose background included both combat experience and engineering training. Sterling had commanded a tank battalion in North Africa before being reassigned to developmental work at Aberdeen Proving Ground. His combat experience had given him first-hand knowledge of how Sherman tanks failed under fire. His engineering background allowed him to evaluate Elmore's metallurgical arguments on their technical merits. Sterling authorized a limited test program in September 1943. Chrysler would construct 3 prototype Sherman hulls using welded plate construction while maintaining normal cast hull production. These prototypes would undergo the full range of ballistic testing, stress analysis, and durability evaluation normally required for any major modification to tank design. If the welded hulls showed meaningful advantages over cast construction, and if production challenges could be resolved, then larger-scale conversion might be justified. The testing protocol reflected both the promise and the skepticism surrounding Elmore's proposal. Aberdeen technicians would fire anti-tank weapons at both cast and welded hull sections, comparing penetration characteristics, fracture patterns, and structural integrity after impact. They would subject complete hulls to stress testing that simulated the mechanical loads tanks experienced during combat operations. They would evaluate weld quality using both destructive and non-destructive testing methods to identify any systematic weaknesses in the welding process. As autumn 1943 arrived and the first prototype welded hulls took shape in Chrysler workshops, the outcome of this competition between casting and welding remained uncertain. American tank crews continued fighting in Sherman tanks with cast hulls, facing German weapons that were becoming more lethal with each passing month. The question of whether a civilian metallurgist's unconventional proposal could save American lives would be answered not by theory or bureaucratic process, but by the harsh mathematics of steel under stress and the unforgiving reality of combat, where survival often depended on modifications measured in fractions of an inch and degrees of metallurgical refinement. The first welded Sherman hull emerged from Chrysler's experimental workshop on October 12, 1943. The structure weighed 38 tons, identical to cast hull specifications, but its appearance revealed the fundamental difference in construction philosophy. Where cast hulls showed the smooth, flowing lines of molten steel shaped by molds, the welded hull displayed sharp angles and visible seam lines where individual armor plates had been joined. Each seam represented a potential failure point that would require validation through testing more rigorous than any cast hull had ever endured. Elmore supervised the hull's transport to Aberdeen Proving Ground with the anxiety of an engineer whose theories were about to collide with experimental reality. The welding process had consumed 6 weeks, far longer than the 3 days required to cast a traditional hull. Each seam had been executed by certified welders using specialized electrodes designed for high-strength steel. The welds had been X-rayed, stress-tested, and visually inspected to standards that exceeded normal production requirements. But no amount of peacetime testing could fully replicate the violence that shaped charge weapons delivered in combat. The Aberdeen test protocol began with conventional anti-tank rounds to establish baseline penetration characteristics. Technicians fired 75mm armor-piercing shells at both cast and welded hull sections from ranges between 500 and 1,500 yards. The results showed no meaningful difference in penetration resistance. Both hull types defeated rounds at angles and ranges predicted by armor specifications. Both showed similar failure patterns when rounds achieved penetration. The conventional weapons that had defined anti-tank warfare since 1939 revealed nothing to distinguish welded construction from casting. The shaped charge testing told a different story. When technicians fired captured German Panzerfaust rounds at cast hull sections, the warheads penetrated as expected, creating holes approximately 3 inches in diameter, surrounded by petaling and spalling. But examination of the hull sections revealed fracture lines extending 6 to 8 inches from the impact crater, following stress patterns invisible to the naked eye but clearly defined by the casting's internal structure. Under magnification, these fractures showed the crystalline boundaries where molten steel had cooled unevenly during the casting process. The welded hull sections showed penetration holes of similar size when struck by identical Panzerfaust rounds, but the fracture patterns differed fundamentally from those in cast armor. Instead of propagating along random stress lines created by uneven cooling, the cracks followed predictable paths determined by the rolled steel's grain structure. More significantly, the fractures terminated at weld seams rather than continuing across the hull. The welds, properly executed, acted as barriers to crack propagation, containing damage within individual armor plates rather than allowing failures to cascade across the entire structure. Colonel Sterling examined the test results with the focused attention of an officer who understood that data translated into crew survival rates. The welded hull sections showed 35 to 40% less total fracturing than cast sections when subjected to shaped charge impact. This reduction in structural damage meant that tanks could potentially survive multiple hits without catastrophic hull failure. Crew members might live through engagements that would kill them in cast hull vehicles. However, the production challenges that had concerned manufacturing engineers proved as significant as predicted. Welding thick armor plates required precise heat control to prevent warping that could throw the entire hull out of dimensional tolerance. The welders needed to maintain specific temperatures, travel speeds, and electrode angles across hundreds of linear feet of seams. Any deviation from optimal parameters could create weak points that would fail under stress. Quality control procedures required X-ray inspection of critical welds, adding time and expense to manufacturing processes that had been optimized for speed. Lieutenant James Bradford, an ordnance officer assigned to evaluate production feasibility, calculated that converting Sherman hull manufacture to welded construction would require 6 months of tooling changes and worker training. During this transition period, hull production would drop by approximately 60%, creating a shortage of replacement tanks that could cripple armored operations in Europe. The strategic cost of improved hull survivability might be fewer tanks available when and where combat commanders needed them. The debate within Army Ordnance reflected competing priorities that had no clear resolution. Combat reports from Italy and the Pacific demonstrated that German and Japanese infantry anti-tank weapons were inflicting tank losses at rates that threatened to exceed replacement capacity, regardless of hull construction methods. American armor needed both better protection and higher production volumes, goals that appeared mutually exclusive given existing manufacturing infrastructure. Elmore proposed a compromise that would later be recognized as operationally brilliant despite its technical limitations. Instead of converting all Sherman production to welded hulls, manufacturers could produce both types simultaneously. Cast hulls would continue flowing from existing foundries at current rates, ensuring that armored divisions received adequate replacement vehicles. New welding facilities would be constructed to produce welded hulls in numbers that increased gradually as workers gained experience and procedures were refined. Combat units would receive mixed inventories, with welded hull tanks deployed to units facing the highest concentrations of German infantry anti-tank weapons. The proposal required investment in new manufacturing capacity rather than conversion of existing facilities, adding cost but preserving production volume. It accepted that some American tank crews would continue fighting in cast-hull vehicles while others received improved welded hull protection. This inequality troubled officers who believed that all American servicemen deserved the best equipment available, but operational reality demanded compromises between ideal protection and adequate availability. General Gladian Barnes, Chief of Army Ordnance Research and Development, approved limited production of welded hull Shermans in January 1944. Chrysler received authorization to construct new welding facilities capable of producing 50 welded hulls monthly by June 1944, scaling to 150 monthly by year's end. The modified production plan maintained total Sherman output while gradually increasing the percentage of tanks with improved survivability against shaped charge weapons. The first production welded hull Sherman, designated M4A3E8 to indicate its experimental status, rolled off the new Chrysler welding line on April 3, 1944. The tank carried the W suffix that had become associated with wet ammunition stowage, but internal documentation added a second notation indicating welded hull construction. To external observers, including German intelligence services, the vehicle appeared identical to standard Sherman production. The distinctive weld seams were hidden beneath paint and, in combat conditions, by mud and camouflage that obscured surface details. Tank crews designated to receive the new vehicles during May 1944 training cycles noticed little difference in operation. The welded hulls weighed the same as cast versions, exhibited identical mechanical characteristics, and required no changes to standard crew procedures. Maintenance personnel noted that battle damage repairs might be easier on welded hulls, where damaged sections could be cut out and replaced rather than requiring complete hull replacement. But the fundamental advantage, improved resistance to shaped charge fracturing, remained invisible until combat testing validated what Aberdeen experiments had predicted. The Normandy invasion brought welded hull Shermans into combat for the first time during the early July operations around St. Lo. Lieutenant Michael Torres of the 2nd Armored Division commanded one of the first welded hull tanks to engage German forces in the dense hedgerow country where infantry anti-tank weapons dominated tactical situations. His crew had received no special briefing on their tank's construction, understanding only that they operated as standard Sherman with standard capabilities and standard vulnerabilities. Torres's first encounter with German Panzerfaust teams occurred on July 8th during an advance through hedgerow country where visibility rarely exceeded 100 yards. A German-shaped charge warhead struck his tank's right hull side at 90 degrees, the optimal angle for penetration. The explosion created the familiar thunder crack that tank crews had learned to associate with potentially fatal damage. Torres ordered immediate evacuation, expecting his tank to be disabled or destroyed. Recovery teams reached the knocked-out Sherman within 3 hours, finding the hull penetrated but structurally intact. The Panzerfaust had created a hole approximately 3 inches in diameter, but fracturing extended only 4 inches from the impact crater before terminating at a weld seam. The crew compartment had been damaged by the penetrating jet, but the hull itself remained sound enough for field repair. Within 2 days, Torres was back in combat in the same tank, now carrying additional sandbags around the lower hull to provide standoff distance that might deflect future-shaped charge impacts. The pattern repeated across units equipped with welded hull Shermans during the summer 1944 fighting in France. Tanks struck by Panzerfaust or Panzerschreck rounds showed penetration but survived with repairable damage at rates significantly higher than cast-hull vehicles. German after-action reports began noting, with puzzlement, that some American tanks appeared to survive multiple infantry anti-tank hits that should have destroyed them. Wehrmacht intelligence analysts theorized that Americans had developed improved armor steel or modified their hull construction, but failed to identify the specific changes that made the difference. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical implications extended beyond simple survivability statistics. Tank commanders operating welded hull Shermans reported increased willingness to advance through areas where German infantry anti-tank teams were suspected. The knowledge that their tanks might survive a Panzerfaust hit, even if disabled temporarily, changed risk calculations that influenced tactical decisions. American armor became more aggressive in close terrain, where earlier doctrine had emphasized caution due to vulnerability to infantry weapons. German responses to American tactical evolution revealed the cumulative impact of multiple Allied improvements to Sherman design. By autumn 1944, Wehrmacht forces faced American tanks with wet ammunition stowage that prevented catastrophic fires, welded hulls that resisted shaped charge fracturing, and increasingly effective tactics that minimized exposure to German anti-tank guns. The dominance that German armor had enjoyed during early war years was eroding under the combined pressure of American industrial capacity and incremental engineering improvements. However, the welded hull program faced challenges that threatened to undermine its effectiveness. Production schedules slipped as welding facilities encountered quality control problems that had not appeared during prototype construction. Some welds failed inspection due to incomplete fusion, hydrogen porosity, or stress cracking that appeared during post-weld heat treatment. These failures required rework that slowed production and raised questions about whether welding techniques could achieve the consistency required for mass manufacturing. Technical Sergeant James Morrison, now assigned to tank recovery operations in France, documented cases where welded hull tanks had suffered catastrophic failures when poorly executed welds gave way under combat stress. In one incident near Metz in September 1944, a welded hull, Sherman's lower side seam, separated when struck by a Panzerfaust, creating a hull breach far worse than the shaped charge penetration itself. Investigation revealed that the weld had been executed with incorrect electrode type, creating a seam that was brittle rather than ductile under shock loading. The quality control crisis threatened the entire welded hull program. During October 1944, Army Ordnance temporarily suspended deliveries of welded hull tanks while investigators examined production procedures at all facilities. The inspection revealed systematic problems in welder training, inadequate supervision of critical seams, and insufficient quality control documentation. Some welders had been assigned to armor work after brief training periods that left them unprepared for the demanding requirements of tank hull construction. Elmore returned to production oversight, implementing revised training protocols that extended welder qualification from 2 weeks to 6 weeks. He established mandatory X-ray inspection for all primary structural welds and required that welding supervisors personally approve critical seams before work proceeded to subsequent construction phases. The changes slowed production, but eliminated the quality failures that had nearly destroyed confidence in welded construction. By January 1945, welded hull production had recovered to planned levels, with quality control problems resolved through improved procedures and better training. Approximately 8% of Sherman tanks reaching combat units carried welded hulls, a proportion that would gradually increase through the war's final months. The distribution remained uneven, with priority given to units facing heavy concentrations of German infantry anti-tank weapons in urban and close-terrain fighting. The winter battles in the Ardennes demonstrated both the advantages and limitations of welded hull construction under the most demanding combat conditions. Staff Sergeant Robert Hayes, now commanding a welded hull Sherman after his earlier experiences with wet ammunition stowage, found his tank surrounded by German infantry during fighting near Bastogne on December 22nd. Over the course of 6 hours, his Sherman took 4 separate Panzerfaust hits, each penetrating the hull but failing to cause structural collapse that would have forced permanent abandonment. Hayes and his crew survived by evacuating after each hit, waiting for German infantry to move past, then returning to their damaged but functional tank. The welded hull absorbed punishment that would have destroyed a cast hull vehicle after the second or third hit. When American forces relieved Bastogne and recovery teams examined Hayes's tank, they found 4 penetration holes, extensive internal damage, but a hull structure that remained fundamentally sound. The tank was rebuilt and returned to service in late January 1945. German intelligence services continued struggling to understand why some American tanks showed dramatically improved survivability against shaped charge weapons. Captured Sherman hulks examined by Wehrmacht technical teams revealed both cast and welded construction, but German analysts failed to correlate hull type with survivability rates. Their reports noted variation in American tank resistance to infantry anti-tank weapons, but attributed the differences to combat conditions, crew skill, or random chance, rather than systematic engineering modifications. The intelligence failure extended to German tank design, which never incorporated welded hull construction, despite clear evidence that some American tanks were surviving multiple shaped charge hits. German armor production continued using cast hulls and, in later models, interlocking plate armor that offered improved protection against kinetic rounds but showed no enhanced resistance to shaped charge fracturing. The engineering approaches that American and German industries took diverged increasingly as the war progressed, with Americans focusing on crew survivability and Germans emphasizing offensive firepower and armor thickness. The final months of the European war brought welded hull Shermans into the grinding urban combat that characterized Allied advances into Germany itself. The rubble-choked streets of German cities created ideal conditions for infantry anti-tank teams who could approach within feet of Allied armor before firing. In these environments, the difference between cast and welded hull construction often determined whether crews lived or died. Staff Sergeant William Hendricks of the 3rd Armored Division experienced the full measure of welded hull survivability during the assault on Düsseldorf in February 1945. His Sherman, one of approximately 200 welded hull tanks now serving in frontline units, advanced through city streets where German Volkssturm militia and Hitler Youth defenders had prepared anti-tank ambush positions in every building and alleyway. The tactical situation forced American armor to accept close-range engagements where Panzerfaust teams could achieve optimal firing solutions against hull sides and rear areas. Hendricks's tank took its first Panzerfaust hit on February 21st while supporting infantry clearing operations near the city center. The shaped charge struck the left hull side at 80 degrees, penetrating cleanly but causing limited fracturing. Hendricks evacuated his crew as doctrine required, then watched from cover as his Sherman failed to brew up in the expected fireball. The wet ammunition stowage prevented fire while the welded hull contained structural damage to the immediate impact area. Recovery teams brought the tank to field maintenance that evening, where technicians welded a patch plate over the penetration and returned the vehicle to service within 18 hours. The second hit came on February 23rd during an advance through industrial districts where German defenders had positioned multiple Panzerfaust teams in coordinated ambush sites. This round struck the right hull side, again penetrating but again failing to cause catastrophic damage. Hendricks continued operating his twice-hit Sherman through the remainder of that day's fighting, evacuating only when a third Panzerfaust round struck the rear hull near the engine compartment. The accumulated damage finally forced permanent evacuation, but Hendricks and his crew survived 3 hits that would have destroyed a cast hull tank after the first penetration. The 4th and 5th hits occurred on February 25th, when German forces counterattacked American positions using the same Sherman that maintenance crews had patched and returned to service. Both Panzerfaust rounds struck within minutes of each other, penetrating the hull but failing to ignite ammunition or cause structural collapse. The tank was finally abandoned when mechanical damage from the 5th hit disabled the transmission beyond field repair capability. Recovery teams examining the hulk found 5 separate penetration holes, extensive internal damage, but a welded hull structure that had maintained its fundamental integrity through punishment that would have been unimaginable for cast construction. Hendricks later described the psychological transformation that occurred when tank crews learned their vehicles might survive multiple shaped charge hits. Early in the war, he explained, American tankers approached urban combat with fatalistic acceptance that German infantry anti-tank weapons meant probable death in close terrain. Welded hull Shermans, combined with wet ammunition stowage and improved tactical procedures, had changed those survival calculations. Crews became willing to press attacks through areas they would have avoided in earlier vehicles, knowing that, even if hit, they might evacuate safely and their tanks might be recoverable. German prisoner of war interrogations conducted during March 1945 revealed growing Wehrmacht awareness that American tank survivability had improved beyond what intelligence estimates predicted. Panzerfaust team leaders reported expending multiple rounds against individual Sherman tanks that refused to burn or explode, as doctrine suggested they should. Some German infantry units questioned whether their anti-tank weapons remained effective against American armor, a psychological shift that undermined defensive operations at a time when German forces desperately needed every tactical advantage. The strategic impact of improved Sherman survivability extended beyond individual engagements to affect the broader operational sustainability of American armored forces. Tanks that survived shaped charge hits could be recovered and repaired rather than written off as total losses. Crews that evacuated from disabled but intact vehicles could be reassigned to replacement tanks, preserving training and combat experience that would otherwise have been lost. The cumulative effect of these factors gave American armor a regeneration capacity that German forces, operating with dwindling resources and replacement pools, could not match. Fisher Elmore visited European combat theaters in March 1945, documenting the battlefield performance of welded hull designs under the most demanding conditions imaginable. He examined Sherman hulks showing multiple Panzerfaust penetrations, interviewed crews who had survived hits that killed their counterparts in cast hull vehicles, and compiled statistics proving that welded construction reduced catastrophic hull failures by approximately 60% when subjected to shaped charge impact. The engineering solution that Army Ordnance had initially rejected as impractical was saving American lives in numbers that validated every argument Elmore had made 18 months earlier. The human dimension of those statistics became personal when Elmore met Technical Sergeant James Morrison, whose cast hull, Sherman, had been destroyed by a single Panzerfaust hit near Anzio in 1944. Morrison had survived with severe burns, spent 4 months recovering, then returned to combat commanding a welded hull tank. His second Sherman had taken 2 Panzerfaust hits during the Rhine crossing in March 1945, but Morrison and his crew evacuated safely, and their tank was repaired. The contrast between his 2 combat experiences embodied the transformation that welded hull construction had created for American tank crews. Production statistics, compiled as German resistance collapsed in April 1945, showed that American industry had manufactured approximately 2,300 welded hull Sherman tanks since the program's inception. This represented roughly 12% of total Sherman production during the same period, a proportion limited by manufacturing capacity constraints rather than design limitations. The welded hulls had been distributed preferentially to units facing heavy urban combat or high concentrations of German infantry anti-tank weapons, creating uneven survival advantages that troubled officers who believed all American servicemen deserved equal protection. German technical intelligence documents captured after the surrender revealed the extent of Wehrmacht failure to understand American tank modifications. German reports from as late as April 1945 continued describing Sherman tanks as highly vulnerable to infantry anti-tank weapons, citing ammunition fire rates and hull fracture patterns that had been obsolete since mid-1944. The intelligence failure had led German forces to persist with tactics and weapon deployments based on assumptions that no longer matched battlefield reality. More significantly, German tank design had never incorporated welded hull construction, despite clear evidence that some American tanks showed dramatically improved resistance to shaped-charge weapons. Captured Panther and Tiger tanks examined by Allied technical teams in 1945 revealed that German armor continued using cast hulls or interlocking plate designs that offered no enhanced protection against the focused violence of hollow-charge warheads. German engineering had remained focused on armor thickness and gun performance, apparently never recognizing that hull construction methodology could affect survivability as significantly as protective steel weight. Colonel Henry Sterling, whose support had been crucial to the welded hull program's approval, conducted final assessments of the modification's combat effectiveness during occupation duties in Germany. His analysis concluded that welded hull Shermans showed 72% survival rates when struck by shaped charge weapons, compared to 41% for cast hull vehicles in identical tactical situations. The engineering difference had translated into a survival advantage that saved an estimated 800 American lives while preserving equipment worth over $30 million at wartime replacement costs. The cost-benefit analysis revealed that welded hull construction added approximately $1,200 per tank in manufacturing expenses, including materials, specialized welding equipment, additional quality control procedures, and extended production time. This investment had been recovered many times over through reduced tank losses and improved crew survivability. Yet, the modification remained controversial within Army Ordnance circles, where some officers continued arguing that resources devoted to welded hull production would have been better spent increasing overall Sherman output. Elmore's response to these criticisms reflected his understanding that engineering success was measured not in production statistics, but in lives preserved. Each tank crew that survived a Panzerfaust hit in a welded hull, Sherman represented validation of design decisions made under time pressure with incomplete information. The metallurgical principles that had guided his initial proposal, the recognition that continuous rolled steel plate offered advantages over cast construction when subjected to shaped charge impact, had proven sound under the most rigorous testing possible. Combat against an enemy, fighting for survival. The broader implications of welded hull development extended beyond World War II to influence post-war tank design across multiple nations. Allied technical intelligence teams shared information about improved hull construction methods with military services that would face similar threats in future conflicts. The recognition that hull construction methodology affected survivability as significantly as armor thickness or chemical composition reshaped engineering approaches to armored vehicle design for decades following the war's conclusion. Soviet tank development, despite receiving extensive technical intelligence about American innovations, showed no immediate adoption of welded hull construction. Soviet armor continued using cast hulls through the 1950s, reflecting different design priorities that emphasized production speed and ease of manufacture over crew survivability optimization. The divergence between American and Soviet approaches to tank construction would persist through the Cold War era, creating fundamental differences in how the two nations balanced offensive capability against protective systems. The memorial ceremony for tank crews killed in the European theater took place at the American Military Cemetery in Luxembourg during June 1945. Fisher Elmore attended, standing among rows of white crosses that marked the graves of men who had died in Sherman tanks before improved survivability modifications reached combat units. The ceremony honored all fallen tank crewmen, but Elmore understood that some of those deaths might have been prevented if welded hull production had begun earlier or scaled faster. Engineering innovations, no matter how effective, always arrived too late for some of those they were meant to protect. Staff Sergeant William Hendricks returned to the United States in August 1945, carrying physical scars from the 5 Panzerfaust hits his welded hull Sherman had absorbed during the Düsseldorf fighting. His survival, along with that of his crew, embodied the cumulative impact of multiple engineering improvements that had transformed Sherman tanks from vehicles with questionable survivability into armor capable of withstanding punishment that would have been unthinkable in 1943. Hendricks wrote to Army Ordnance describing his experiences, providing detailed accounts of shaped charge impacts and structural responses that would inform post-war analysis of combat effectiveness. The final production statistics, compiled in September 1945, showed that welded hull Sherman tanks had achieved ammunition fire rates of 11% when penetrated by enemy weapons, compared to 15% for cast hull vehicles with wet stowage and 63% for early war Shermans with cast hulls and dry ammunition storage. The combined effect of improved ammunition protection and enhanced hull construction had reduced tank crew casualties by approximately 78% compared to early war models. This represented one of the most successful combinations of incremental engineering improvements achieved by any combatant nation during World War II. German post-war technical assessments, conducted by former Wehrmacht engineers working under Allied supervision, revealed belated recognition of how completely American tank survivability had improved during the war's final 18 months. German analysts noted that their intelligence services had failed to identify specific modifications that transformed Sherman vulnerability profiles, leading to persistent tactical errors that wasted limited German resources attacking enemy weaknesses that no longer existed. The intelligence failure had contributed to German operational defeats at a time when accurate threat assessment was critical to maximizing the effectiveness of dwindling military capabilities. Fisher Elmore returned to civilian metallurgical work in 1946, his contributions to tank survivability recognized within engineering communities but largely unknown to the general public. The welded hull program represented applied engineering translated into practical solutions for human survival under combat stress. His recognition that cast construction contained inherent limitations when subjected to shaped charge weapons had saved hundreds of American lives while providing tactical advantages that enemy forces never understood or effectively countered. The legacy of welded hull development extended into post-war American tank design, where the principles Elmore had championed became standard practice for armored vehicle construction. The M26 Pershing, M46 Patton, and subsequent American tank designs all employed welded hull construction, reflecting institutional acceptance that this methodology offered advantages that justified its higher manufacturing complexity. The engineering revolution that had begun as a controversial proposal from a civilian metallurgist became foundational to American armor doctrine for generations following World War II. Lieutenant Colonel Daniel Erickson, whose initial report on cast hull fracturing had sparked the welded hull investigation, reflected on the program's success during his retirement in 1963. The modification had succeeded, he noted, not through dramatic technological breakthroughs, but through systematic application of established engineering principles to specific combat problems. The recognition that tank hulls could be improved through construction methodology changes rather than simply adding protective weight had opened possibilities that conventional military engineering had overlooked. The human cost of the delay in implementing welded hull construction remained a source of regret for those involved in the program's development. Hundreds of American tank crewmen had died in cast hull Shermans during the months when welded hull technology was being tested, refined, and slowly scaled into production. Each of those deaths represented a time when improved protection existed in theory, but had not yet reached the battlefield. The inevitable tension between engineering perfection and operational urgency had been resolved through compromises that saved many lives but came too late for some. The quiet revolution in tank survivability, achieved through welded hull construction, combined with wet ammunition stowage and improved tactical procedures, transformed Sherman tanks from vehicles that German intelligence considered vulnerable into armor that could survive multiple shaped charge hits. The engineering modifications that military bureaucracy had initially dismissed as impractical, expensive, and unnecessary had proven decisive in preserving American lives and maintaining operational effectiveness during the war's final, most brutal phase. In museums and memorial sites across the United States and Europe, restored Sherman tanks stand as testimony to the industrial capacity and incremental innovation that characterized American military production during World War II. Some of these vehicles carry the visible weld seams that mark welded hull construction, physical evidence of the engineering revolution that saved hundreds of tank crew lives through systematic application of metallurgical principles to combat survival problems. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.